Hey, Plumber Tom here. If you're preparing for a plumbing state test or trying to improve your knowledge of code and understanding of plumbing, don't forget to check in the description below for links to study guides, online courses, and other resources that will help you to learn the code and pass your test. When you click on those links and purchase resources, you're helping me to be able to create more great content. Thanks for watching. NFPA 13D, standard for the installation of sprinkler systems in 1 and 2 family dwellings and manufactured homes. Hello, welcome to this presentation of the NFPA 13D. My name is Thomas, and in this presentation we're going to finish off the book. We're going to go from chapter 10 to chapter 12. We'll see what we can learn. Let's get into it. Now that you have your book, join me in chapter 10, and we're going to look at discharge and hydraulic calculations. What does that really mean? What we're talking about is design and sizing of the system so that it can deliver the amount of water needed to put out a fire. 10.1 is about design discharge. 10.1.1 says that we have to provide at least the amount of flow required to produce a minimum of 0.05 gallons per minute. Obviously, you need enough water flow to be able to make the head do its job. 10.1.2 talks about the water supply, and if the water main in the street is 4 inches or larger, then the static pressure can be used when we're calculating our sizes. Now, we need to know the pressure of the system in order to calculate pipe sizes. But there's that variable. If you're on a well and you don't have a 4-inch main, you're going to have to factor in different things to make sure you have adequate pressure. Whereas they figure if you have a big main out there, 4-inch, plenty of volume, then we can just go with that static pressure being delivered from that main in the city. This saves a little bit of calculation when we look at the water source. 10.2 is an important one, and it's very simple. It gives us the number of design sprinklers. They say at a maximum, we should have 2 in any room or compartment. Now, why only 2? Well, if you'll remember, these systems are designed basically for one head opening in one place at a time. If you get too many heads open at the same time, then the system won't be able to deliver enough water to do the job. So generally, in any room or compartment, you're going to have one head, and when that goes, it should be enough to cover the fire-affected area. Now, you get into larger rooms or compartments, and you can start to add, but they say, in general, you'd want to have only a maximum of 2. Now, please keep in mind, we're dealing specifically with residential fire sprinkler systems. You can imagine a big warehouse where you see 20 heads in one space. Yeah, that's a different sizing in the NFPA 13, not the 13D. We're looking at a residential setting. We're looking at compartments or rooms that are not going to be enormous, and that's where coming right back to 10.2.1, 2 is going to be your maximum in any of those spaces. You'll have to place those heads in an appropriate way so that they're going to do the most good and avoid obstacles, as we looked in chapter 8. But 2 is the maximum number. Let's have a look at a couple of diagrams. These are in the appendix 10.2. And they give us a floor plan with different arrangements of ceilings or walls that create different compartments. Have a look at this floor plan. We have a dining room and a kitchen. The dining room opens into a living room, and then there's a hallway that goes off to the left. Notice it says that these openings have a maximum 8 foot in a single wall. They have lintel into the hall. That means the ceiling actually dropped down. And when you have lintel, that creates this compartment of the living room. It's an individual compartment. But what happens if we have a different arrangement? Say into the dining room, it opens all the way up to the ceiling. There's no lintel, there's no doorway, it's just open. Then the dining room and the living room become one compartment area, and we have to calculate or figure sprinkler placement to be able to catch both of those. Notice on the right side, we still have an 8-inch lintel, and that's going to separate out the hallway as a different compartment. But in the third diagram, that lintel's been removed. So now we have dining room, living room, and hallway, and these are all adjoining spaces. And we got to figure out, like, where are we going to put fire sprinklers in a way that is going to be able to put out the fire. So these are just some design considerations to think through. You can see how, as we're looking around the compartments, where to place sprinklers, those are some variables that we have to factor in. Now 10.3 refers us to some pipe configuration. We've seen this several times as we've looked through the NFPA 13D, but you can have, as a reminder, a looped system where it circles around, a gridded system, a straight run with branches, or a combination of different configurations. So that's listed again in 10.3. 10.4 brings us to pipe sizing. And it says, for specially listed piping products, friction loss for the pipe and fittings shall be permitted to be calculated based on manufacturer's data. So we're going to talk through some of the considerations for pipe sizing, including 10.4.2.1, which gives us some minimum. The minimum pipe size for any steel pipe is going to be 1 inch. If you get into pipes other than steel, that's 10.4.2.2, you can run 3/4 inch. And then there's 10.4.2.3. It gives us sizing conditions for special fittings. The minimum is going to be 1/2 inch. So this establishes some real baseline, very minimums on what pipe sizes can be run for these systems. 10.4.3 gives us some pipe sizing techniques. There's a number of different ways that you could go about this, and there are 4 approved ways that they give right here in the code. It says, first of all, you have the simplified calculation method. Second, there is a prescriptive pipe sizing method, and we'll look at some examples of these, although we're not going to go in depth and do like an all-out sizing. In general, I think if you understand what sizing methods there are and basically how those work, then that's probably enough for plumbers' knowledge. The third one there is hydraulic calculation procedure from the NFPA 13. Now we're in the 13D, that's just for residential, but the 13 is for all fire sprinklers in general, so that should apply pretty well here, right? And then the fourth option is the manufacturer's listed installation instructions. So if a system manufacturer has a sizing method for you, then you can use that as well. Have a look at this simple illustration of pipe sizing. This is coming from the fire protection specialists. You can reach them if you want to order or get more information about fire sprinklers, but this diagram illustrates a table here taken from the NFPA 13, and you've got pipe sizes listed down the left with the number of sprinklers that can be put onto those respective sizes on the right. Notice for a 1-inch pipe, you can do 2. As you go to 1 1/4, 3, 1.5-inch pipe, 5, and so on. You can see how as the pipe gets bigger, there is going to be a limit to how many sprinklers are attached to that, but then you know what pipe sizes you would need depending on the number of sprinklers. Here's another illustration where we have the maximum number of sprinklers on a branch. This is also from the fire protection specialists, but you see on the right side some larger pipe sizes, 2-inch, 2.5. And then on down, you can see as the sprinkler heads are installed, the pipe sizes can reduce for each of those branches. So this is the NFPA 13 sizing. Again, this could work for your residential side, but this gives you kind of an idea of how those pipes are going to be configured in relation to the number of heads connected. Let's look at 10.4.4, which is general pipe sizing method, and it gives us step-by-step on the things that we need to do in order to size fire sprinklers for residential. Let's go through the steps real quick. Follow me here. Step 1, establish the system flow rate. We need to know what is going to be required for flow. Step 2, determine the water pressure in the street. Now you remember we talked about the 4-inch main. If it's big enough, we'll just take the pressure as it is. If I'm dealing with something else like a well, I'm going to have to come up with a water pressure from that system. Number 3, you select a pipe size. In this pipe sizing method, you kind of guess first. You say, okay, well, what if I use this pipe size? Is it going to work? And then we're going to do deductions from there. So we choose a pipe size and say, okay, let's see if this fits. Step 4, you would deduct pressure loss for the meter. Step 5, deduct pressure loss for the elevation. So if it climbs up 20 feet from the basement up to the top, you're going to have to deduct for those losses. Step 6, deduct pressure loss from the city main. Step 7, deduct pressure loss for piping in the building. Now we're actually subtracting for the friction losses inside the pipe, inside the building. Step 8, deduct pressure loss for valves and fittings. So we're subtracting off anything that water passes through, valves or fittings. Step 9, you repeat the sizing for each floor. Step 10, we determine if the remaining pressure is too low, then we have to start over, pick a different pipe size, and redesign. Seems kind of backwards. Step 11, if the remaining pressure is too high, you can calculate for smaller pipes. So you're kind of trying to find the middle where it's not too low of pressure or too high, but your leftover pressure should be enough when you're done. And once you find that medium, then you're on step 12 and you've got your pipe size. So I don't know, that seems a little bit different. That's the steps that are given to us. Pick your pipe size, deduct a whole bunch of pressures, see if the pressure is going to meet what's required. There are some tables in here that help when it comes to calculating those pressure losses. There's a table for pressure loss through meters, a table for pressure losses through fittings and valves in steel, pressure losses for fittings and valves in type K copper, pressure losses for fittings and valves in type L copper, pressure losses for fittings and valves in type M copper. Please notice that the pressure losses are measured in equivalent length of feet. For fittings, valves, or other deductions, on the left side of these tables, you'll notice the diameter of the pipe. Pipe sizes are provided with a particular length that they can travel and still deliver water at a given pressure. This deduction of feet would limit the distance or then adjust the pipe size according to these friction loss deductions. Does that make sense? Please take a moment to notice the available pressure equation listed in 10.4.9.1. This is a simple equation. It's just subtraction. It looks long, but it's not so bad. The point of this equation is to find the pressure difference that will offset the friction losses in all of these things listed. We start with P sup, the pressure available from the supply. Then we have PL sv, which is the pressure loss in the water service pipe. Then we have PL which is the pressure loss in the meter. Then we have PL which is the pressure loss in devices other than the meters, softeners or PRVs or whatever. And then we have PL which is pressure loss associated with the elevation. And finally, PL which is maximum pressure needed at the heads. Take those all off, subtract them, and that's going to account for friction losses and give us the pressure we need. Let's go another route, shall we? 10.4.9.2 gives us the prescriptive pipe sizing method. It's a little different, a few less steps. Let's see what it takes. Step 1, you determine your supply pressure. Once again, we're starting with what kind of pressure are we getting that we can use. Step 2, determine the pressure loss for the service pipe. So now we start deducting pressure loss for the service pipe. Step 3, determine pressure loss from the meter. Step 4, determine pressure loss from devices. That's pressure reducing valves, backflow preventers, water softeners, water filters, anything that water has to pass through on its way to a sprinkler. Those things are going to cause restriction and have to be deducted. Number 5, determine pressure loss due to elevation difference. So once again, from the basement all the way up to the second floor, what are we going to lose? Step 6, determine maximum pressure required by an individual sprinkler. So now I look at the sprinkler and say, this is what is needed. We can calculate the pressure that's available in step 7 and determine, am I delivering enough pressure for that sprinkler head? And in step 8, I determine the maximum available pipe length. There are tables that would be used here for each of those. If we're using the prescriptive method, there's going to be a number of tables that we would use for that. Water service pressure loss table. There's the elevation loss table that'll help me to know, like, for however many feet, this is what I've got to subtract. And then there are tables for allowable pipe lengths for different types of sizes. So basically you would pick a size, say 3/4 or 1 inch, go to the table and see if that's going to be enough pipe to get you where you need to go. On the left side of these tables, you got your flow rate. That's what's required. Then you've got a column for the sprinkler size. That's all the same because we come to this, it's a 3/4 table. We come across there and we see, like, here's the distance it's going to go. You come up to the top and find out, well, is this enough pressure for the head or not? If not, we'd have to go to a different size. We see the similar table for different types of pipe. This one's for type M copper. So in summary, as we look at chapter 10, basically you need to know about your pressure. You need to know the sprinkler and what needs to be delivered. Then you can use different sizing methods to be able to figure out if that's going to work. And hopefully that's enough of an introduction to those sections on sizing to help you kind of figure out how that works. Let's go on to chapter 11. Chapter 11 gives us some information about system acceptance. This would be at the point when I've got the system in, it's ready for use, but it needs to be accepted by those who have authority to give me, it's basically inspection, right? Check me off here. So in general, the installer is required to perform the acceptance tests prior to asking for approval. So if I want this thing to get checked off, I need to do the tests. I need to have that inspected. Then I can get approval. Then the AHJ, or authority having jurisdiction, must be present when the tests are performed to accept the system. This is the inspection, right? They show up, they look it over, they say, okay, you've passed these tests. This system is now acceptable. 11.2 gives a little more specifics on the acceptance tests. It requires a hydrostatic test. That means you put water in, pressurize that up. It has to hold water for 2 hours with no gauge drop or any visible leaks. You can use plugs rather than sprinkler heads. If you're going to test where those heads would be, just plugs can be used. And the heads can be installed later when the building is ready for finish. But ultimately, it does state that all those plugs have to be removed and replaced with fire sprinkler heads. You can use a pump test. That's going to pump pressure into the system and create the hydrostatic pressure. And then it also talks about system operation tests. So if we're using different type of system, like a pre-action system, a dry pipe, a double interlock, those types of systems have tests where you would have to make sure that you can demonstrate those systems are working properly in order for the system to be accepted. Let's move on to chapter 12. It is titled Inspection, Testing, and Maintenance. There are a few important things to understand from chapter 12. In general, it says that the installer is to provide the owner or occupant with instructions of inspecting, testing, and maintaining the system. A fire sprinkler system is not something that you just install and walk away and never look at again. It does need to be periodically tested to ensure that it's functional, so that if there's a fire at any point, it's going to do its job. There will be some instructions for that, and since the fire sprinkler installer is going to be long gone whenever there's a fire, that information needs to be left with the owner. 12.2 talks about inspections and tests, and we're not talking just about the acceptance, the initial inspection that checks it off. We're talking about these periodic tests. It says sprinkler systems are to be inspected and tested periodically. No, it doesn't give a specific time frame. It doesn't say monthly, it doesn't say yearly. It just says periodically. So I don't know the exact recommendation there, but definitely on a routine basis, the system should be checked to make sure it's working. 12.3, maintenance. The system would have to be maintained according to the manufacturer's instructions. Any damaged components of the system should be replaced. So if you have a sprinkler head that has a bent deflector or something like that, those would need to be replaced and kept up so that the system is in its fully operational condition. 12.3.3 reminds us of the rule that we cannot paint or decorate or do anything to the heads. They need to be left alone, left as is. Sprinklers, escutcheons, that's the nice trim that goes around it, or cover plates are not to be painted. You can install them after paint. You can mask over them so they don't get painted, but they should not get paint on them. Painted sprinklers and escutcheons or cover plates are to be replaced. So, you get people in there doing remodels. They don't know any difference, so they just paint over everything. That's not going to work. Those heads would have to be replaced. We'll wrap this chapter up with summary of 12.3.4, talks about wet pipe systems, and they have to be maintained above 40 degrees. We talked about that in our Chapter 9 presentation. 40 degrees the limit for a wet pipe system. If the interior space isn't kept to that, we have to look at other alternatives, whether it's antifreeze or dry pipe system. If it's antifreeze, 12.3.5, antifreeze systems have to be maintained. There are certain requirements for that. They have to be periodically tested to ensure that the antifreeze is still a good mix. If the antifreeze isn't good, then it has to be replaced. So periodic testing of the antifreeze itself is required with tags indicating when those tests took place. And finally, 12.3.6, the 2025 goes over some inactive system options. And with that, I want to congratulate you for sitting through all these presentations on the NFPA 13D. I've taken you from Chapter 1 to Chapter 12. I've tried to bring in as many appendix illustrations and other comments as I could. Hopefully this serves as a good overview of the NFPA 13D for those of you, especially who are preparing for a state test that will involve questions from this code. Thanks again for watching. Good luck to you as you continue your study of the NFPA 13D. I'll see you next time.